a lot of quantifiers. Yes?
And how do you get the parameterized function?
Yes, this is exactly the next slide. There are plenty of possibilities how we could try to define such a parameterized function over the state bits. Here I try to sketch one possibility, namely to define a parameterized CNF formula over the state bits. Remember that a CNF formula, a conjunctive normal form formula, is always a conjunction of disjunctions of variables. And in our case, every variable is either a state variable or the negation of a state variable. And now we use template parameters, they are all marked in blue here, in order to define how our CNF formula looks like. So I illustrated everything here as a circuit, but actually this is formulas which we construct here. So we use a template parameter to decide whether the first clause contains x0 or not x0. Then we use another template parameter which basically decides whether this first clause contains x0 at all or not. And we can do this for every variable. We can also have template parameters which define whether a certain clause is actually used or not used in the entire formula. So once we have fixed concrete Boolean values for all the blue signals here, we have a concrete formula over our state variables, a concrete CNF formula. Certain state bits are negated, certain state bits are unnegated, depending on our choice of all these variables. So this is one idea of how we can construct such a parameterized formula over our state bits. And by fixing values for the parameters, we get a concrete function. By taking other values for the parameters, we get a different function. So this way we can search for values for these parameters instead of search for a function, basically. This is the basic idea. Compared to this learning-based approach, which computes the winning region iteratively, the advantage here is that we need only one core to a QBF solver, or maybe several cores, because we may start with a very small CNF, and only if it doesn't work, we increase the size of the CNF in several iterations in order to save computation time. Also, we have rather small formulas to handle here, only one copy of the transition relation, only fixed two quantifier alternations, but the formulas are only small if our template is small. If our template is huge, then our formulas will also be huge. And this is also the main disadvantages. So one disadvantage is that this approach is not really good at detecting unrealizability, because we may try with a certain template, it fails. Well, we may just not have tried with a large template, a large enough template. So we try with a larger template, it fails. And at no point in time we can conclude that there actually is no solution, no matter how large we pick our template. The other disadvantage is for complex templates we get also very, very complex formulas, and the search space for the solver is also huge. Depending on how the solver fixes the template parameters, it gets completely different winning regions, and the solver has to search through all the winning regions to find one which satisfies our three important properties. So this was the template-based approach. I just wanted to mention this briefly as a completely different approach. Yes. So the conclusion is this only works well if there exists a very, very simple formula that characterizes our winning region. If the simplest formula that characterizes our winning region is super complex, then this approach will not find it, or not find it fast. Let me now, in the end, show you some experimental results we performed in order for you to get a feeling how well these algorithms perform or not perform on certain benchmarks. The first benchmark is an ARM-AMBA bus arbiter. You also have this benchmark, I think, in your benchmarking framework. This can be seen as a really industrial, realistic benchmark. I want to compare here the execution times for the different methods. Again, this is a so-called scatter plot. So the y-axis shows the execution time for the benchmarks, and the x-axis shows the different benchmarks with increasing difficulty. So the steeper a line rises, the worse is its complexity. We already see two lines here. this is a simple BDD-based implementation. Actually, I took the implementation from the group that won the synthesis competition last year as a baseline for our comparison here. We did pretty much the same competition also last year, but last year the students had to implement the tool from scratch, not just optimize an existing one. Also, here is another existing work which also uses SAT solvers. Originally, I also planned to explain this method here in class, but we are already out of time without explaining this, so good that we skipped it. Okay, so these two lines will serve as a baseline for our comparison. Unfortunately, the template-based method does not work at all for this benchmark. For each and every benchmark, it shows 10,000 seconds of execution time, which just means that we killed the tool after 10,000 seconds of execution time. So this approach could not solve any benchmark at all. This QBF-based learning is actually not much better for this benchmark. It could just solve 2 benchmarks and then time out. But when we implement this using SAT solver, as illustrated here, then we already get much better performance. We also developed a heuristic which exploits unreachable states in this computation. With this, we already get kind of close to the performance of BDDs. And we also talked a little bit about the parallelized implementation. So this yellow line here is a parallelized implementation of the same approach using 3 threads in this case. So here we pretty much get the same performance as with BDDs. You could say it's a little bit better here, but it's actually the same. But this is just one benchmark. For other benchmarks, the situation looks completely different. And this is a multiplier, which you also have in your benchmark framework, parameterized with the bit width of the multiplication. Here, kind of all approaches scale equally well. Only this template-based approach is super fast and solves all these 10 benchmarks in basically no time, no matter what the size is. Here is one more. This one specifies a barrel shifter, and it is well known that BDDs are not really good at solving these kinds of benchmarks. So these are very, very simple designs, but they just freak out the BDDs. They just cannot handle this. And this is also what you can see here. BDDs do not work at all. Also our template-based method kind of sucks. But the QBF-based method is much better already. And all these SAT-based methods, they just solve all these benchmarks in basically no time. Less than a second usually. This slide highlights the parallelization speedup we could achieve with our parallelized implementation. This is a so-called scatter plot, which means that the x-axis shows the execution time per benchmark for one thread, and the y-axis shows the execution time for each and every benchmark with 2 threads. So basically, this point here means that with 3 threads, we needed 200 seconds, and with only 1 thread, we needed 8,000 seconds, for instance. So everything which is below this line of equality is good. This is also a logarithmic scale, so small distances mean actually a huge improvement factor. So we can see that with 2 or 3 threads, we actually achieve a speed up of more than a factor of 2 and 3. And the reason is that we use different solvers and slightly different algorithms in the different threads. And these different solvers, they seem to complement each other somehow nicely, so that overall we achieve a superlinear speed up, as it is called.
But do you share information between solvers?
Yes. So each time a solver refines the winning region, it notifies all the other solvers, and also each time a thread, a solver found out that this U is not good, it also notifies this to the other solvers so that every solver can immediately profit from all the information. And I think this is already the end of the presentation. So to sum up, synthesis is usually done with BDDs because they are super convenient. They provide you all the operations like existential quantification, universal quantification you need for implementing synthesis algorithms symbolically. What else? Today we've heard about methods that use QBF and SAT solving in order to implement these algorithms. There we had to do a lot of tricks in order to make them do what we want. Our conclusion is that these set-based methods perform well on certain benchmarks and not so well on other benchmarks, which is never a particularly satisfying conclusion, but unfortunately we could not find the super algorithm which outperforms PDDs on all the benchmarks. The good thing about these SAT and QBF-based approaches is that they can profit from all the recent developments in these SAT and QBF communities, and we must expect that in the coming 10 years these solvers will improve even more in performance, so the synthesis algorithms can profit directly from these developments. In one of the last lectures you will also hear more about synthesis algorithms based on decision procedures like SNP solving. In the end there will be lectures on so-called bounded synthesis and parameterized synthesis, where we will use SNP solvers, as you have heard about in the previous lecture, for synthesis instead of SAT and QBF solvers. And I hope that's it. There are also some references if you are interested in more details. And yeah, thank you for your attention.